Good afternoon. Thank you all for joining this speaker series hosted by the Translational Data Analytics Institute, or TDAI. I'm Dr. Cathie Smith, Managing Director of TDAI. Before we get started today, I'd like to recognize TDAI staff member, Dev Singer, who has worked tirelessly behind the scenes today and other days to organize our speaker series. Her efforts are all in support of TDAI's #1 priority, research, scholarship, and creative expression. So thank you, Dev. Today, I'm delighted that we'll be highlighting the research of two of TDAI's core faculty who joined our community as part of the Discovery Themes Initiative. As you'll soon see, their collective research addresses two related yet distinct areas of research: data security and data privacy. The format for today will be similar to other sessions where our speakers will speak one at a time, and then after each talk, there'll be some time set aside for Q&A. So I'm going to start by introducing Dr. Zhiqiang Lin. Dr. Lin is TDAI core faculty and associate professor of computer science and engineering. His research interests are in systems and software security and trusted computing. His work emphasizes developing automated program analysis, system abstractions, and tools, and then applying them to secure application programs, including mobile apps and the underlying system software. He is recipient of both an NSF Career Award and an Air Force Office of Scientific Research Young Investigator Award. Before coming to OSU, he attended Purdue University, where he received his PhD in computer science. The title of Dr. Lin's talk today is Towards Confidential Computing with Trusted Execution and Environment. Dr. Lin.
All right, thank you. Thank you for the introduction. Good afternoon, everybody. Thanks for coming to the talk. Today, I would like to talk about how to use the hardware features from commodity processors to achieve confidential computing. We're in the era of data economy. Data has become the world's most valuable resources, which used to be the oil. And in particular, data is the is the lifeblood of AI and is the key element that makes our AI so powerful. Without data, you cannot use your facial recognition to unlock your phone or using virtual voice assistant to control your IoT devices. However, data is also under the danger of either being leaked or abused. Over the past several years, we have witnessed numerous data breaches, such as from companies like Uber, Equifax, British Airways, or Marriott, and millions of customers' records gets leaked. Of course, all these companies gets punished with huge amount of fine from the government. Meanwhile, data can also be abused. The well-known examples include the one from Cambridge Analytica. We know this company harvested more than 50 million Facebook users' records, and they use that to build models for customized advertisement. And the consequence for this is Cambridge Analytica run into the bankruptcy, and Facebook received $5 billion of fine from FTC. And we also know today there are laws and regulations get introduced. Certainly this will help solve this problem, but still we need technology. One important technology is the confidential computing. Confidential computing is not new at all, and it has been there for many, many years. And lots of technologies has been developed in this direction. This include multi-party computation, homomorphic encryption, differential privacy, federated learning, and trusted execution environment. In my talk today, I will focus on trusted execution environment. Before diving into deeper to understand what is TEE, let me first explain you why we need a TEE. By the way, TEE is widely available today, and it's available in almost all the commodity processors. If you buy a laptop or desktop today, your computer will come with TEE, and also your phone has TEE as well. So early days, we understand our computer all can be attacked, and there are viruses and antiviruses. And we know when you have viruses, we first build antivirus, and early days we build antivirus in the user space. And of course, viruses are super smart. They can infiltrate to the, they can attack your antivirus. So difference there is, let's build our antivirus, go to the OS kernel. And however, viruses are super smart. They can keep evolving, keep mutating, and they can infiltrate OS kernel and to compromise your operating system kernel, and then compromise your entire system, and then all your documents or everything can be leaked or abused. And later, when what it is called computing, and then people start to build defenses into a hypervisor. And however, we also know that malware or viruses, they are all super smart, right? They just keep infiltrate, and then they can compromise the hypervisor, and then eventually compromise the entire software stack. And then can we still build a reliable defense towards this, right? To defend viruses? Then the solution there is, all right, let's build defense, go to the hypervisor. That is where this TEE technology comes from. You can see here with TEE, malware has to either attack the hardware or just attack the application. So now you can see the attack surface gets significantly minimized. And now you don't have to trust OS kernel, and you don't have to trust hypervisor. You only need to trust the hardware and also your application. So then what is TEE, right? So here I just use an example from the Intel CPU. So basically it's a feature in the hardware, and everything inside the CPU, when you run into this mode, is decrypted. So it relies on cryptographic techniques like encryption, and everything inside the CPU is decrypted. But when you swap, but data in the memory, they're actually encrypted. So, and then malware or even operating system kernels, they cannot read the contents of the data. That is why TEE. I mean, so let me talk about a number of efforts my students I have been working on over the years. Okay, so this morning, I went to my email box to see when did I start to look into this technology. It turns out it is November 2015. We got the SGX laptop, and then with that laptop, we start to programming and understand in detail how it works. And so the first project we did is actually leverage SGX for protection of the computer games. We know computer games often suffered by cheats. So how can we use this TEE to prevent cheats? So we published a paper talk about we can use SGX to protect computer games. And also we look at some other things to protect, such as the computer logs, because log is very crucial. Attacker wants compromise the system, they would like to delete your logs. So how can we use SGX to protect logs? And also SGX suffer side channel attacks. How can we build defenses to defend control side channel? And with a number of colleagues, and we also look into the direction of using SGX for data analytics, like how we secure your data processing. And because I have multiple colleagues working on this, that's why we keep digging into this direction. So we have another work called SGX Bigmatrix. We basically build our abstraction to support big data analytics, especially matrix operation in SGX. And also we build a framework called SGX Elide to support the code secrecy of the enclave code. And after I moved to Iowa State with my colleagues Inchen and his group, he's an expert on side channel analysis. That's why we look into the security, how SGX or this TEE can be attacked. So we look into the problem like speculative execution, and also look at AMD SEV security. And in 2019, we also developed our SDK called Rust SGX to help developers to develop secure programming. This is a collaborative project with industry. So in today's, of course, we still continuous efforts in 2021. We haven't we have a number of papers on the submission. So maybe next time I will share you more details on that work. So in today's talk, I will just focus on those 4 works. And okay, so let's look at the first one, the SGX big matrix. This project basically is focused on how we can use SGX to support big data analytics. As those years, particularly 2016 or 2015, some other researchers already start to investigate how you can leverage SGX to support data analytics. One problem we found is the current architecture with SGX has only limited memory, and you cannot do large-scale data processing. And with my colleagues, Dr. Murata, he's expert on data analytics. So he has a key observation. He found the matrix operations in those data process framework is not well supported. So that's where we're going to. We developed our abstraction called big matrix inside. I mean, by leveraging this platform. So, and we tested this, and the results looks quite promising. You can actually don't see big performance slowdown. The next project is SGX Elite. Basically, the observation there is we found after programmers developed their code, they released their enclave code, and this code is actually not encrypted, and you can still disassemble, can look at either in secrets inside your code. So here is, hey, can we build a framework to support the code confidentiality? That is where this SGX Elite project is about. We basically build our framework and in the toolchain, and then once developers release the code, we can help them to sanitize the code, make sure there's no secret, and meanwhile we can encrypt the code. And we also test the performance. You can see it's actually quite tiny. And the next project is on the Rust SGX. This is a collaborative project with the industry. It was started from my students' internship. And the key observation there is we know the SDK provided by Intel is still built on top of C and C++, and developers can, the enclave code developed from this SDK can still suffer from memory corruptions. So then can we use memory safe languages to help developers develop the code? That is why we look at using programming languages such as Rust. So so eventually, due to our Rust SGX projects, we built our practical and layered approach to exterminate memory corruption for SGX enclave programs. And this is actually a quite large project. Many people get involved. And you can see it's a full-fledged SDK. And today, many developers actually use this one. It's open source. And we test the performance. You can see it's still actually quite promising. And since I don't have much time, that's why today I only briefly touch this. Each of those works, maybe I need 30 minutes to explain you in greater detail. So then let's look at the applications. Sometimes this is how we innovate. We direct the use case and say how we can bridge the gap. So there are many use cases with this trusted execution environment. And one example you can think about is like in a hospital, right? We understand hospital has huge amount of privacy sensitive records, right? And this stopped sharing. And so is it possible to rely on trusted execution environment? Say you can offload your data, right, to our secure cloud, and this cloud is protected by TDAI, and then you could share among multiple parties, such as doctors, insurance companies, or researchers, even in the government, right? By using this TDAI technology, and you can make sure the code is trusted and always. I mean, if you properly engineer that, right? Make sure all this cryptography gets properly handled, the key is not leaked, and so on and so forth. So this definitely could be representative a version of achieving medical record sharing, and. The next one is like a privacy preserving contact tracing. We know last year, right, and many groups have been working on building digital contact tracing system, and this systems, many people would like to use it because of the privacy concern, because they worry about maybe people harvest their data and abuse their data. Fortunately, actually, with TEE, you could encrypt your contact tracing data and offload them to a secure cloud, and then and also verify, like through attestation, make sure that's really the code processes data. So so basically, right, as other people demonstrated, it's completely possible. You can with TEE technology build a privacy preserving digital contact tracing. And the last project basically I want to talk about is how to use TEE to protect computer games. You can see initially I started from this project. This is still something I'm super interested, super excited, and I still have 2 students actively investigate this direction. And we know computer game industry is actually fairly large industry, and it is valued like hundreds of billions of dollars market size. And however, game industry suffer a huge problem, that is a cheating problem, because players oftentimes, right, they can easily find cheats to modify the games to gain advantage. And you can see here, even says 37% of game players they commit some kind of cheating. And then as an example of the cheats, you can imagine, you can game players can often find cheats. Like for example, here, assume you're playing games, you want to modify the games and then gain your advantage. For instance, like this game player, he can change the maybe game currency, right, from 100 to 1,000. So so here the question is, hey, can we stop this? How can we deal with this? This is a similar situation like your data. When you upload data to the cloud, how can we make sure you cannot tamper with the data, right? And also make sure this is really the code that operates with this data. So this is a huge challenge. That's why I love this example, and I hope I'm keeping investigating, and I hope eventually we can solve this. So maybe let's also zoom in on a little bit detail, right? What are the challenges, right? As I said, the anti-cheating is a huge problem in the in the game industry, and so there you have to make sure the data integrity, like the digital assets in the memory. You make sure attackers or game players or cheat engines, they cannot modify the data in the memory. And also you also want to make sure the code is really the code you released. There is no malware or virus, right, or attackers, they didn't modify the game player's code. So make sure data integrity, and also make sure code integrity. Like I said, right, you release your game, computer games, and make sure that is really the game you released, because once game players or attackers got the game, they can disassemble the code, they can patch the code. That's how they gain advantage. So these are the key problems there, and if you also zoom in to say, hey, how we can make it practical, right? And if you really say let's adopt TEE for anti-cheating, then there are multiple challenges you have to solve. You can imagine each different games have different secrets, different resources, and then you have to understand the particular secrets in the game. You have to perform program analysis, and also the SGX, the particular example Intel, if you use SGX to achieve this, if you focus on the new games, the games you want to develop from scratch, there you have to partition the software to trusted components, untrusted components, because SGX Enclave has only limited memory. And also, what about legacy games? I don't have the source code of the games. Can I still develop solutions to protect the code integrity and data integrity? And also the IO is actually not being protected by the TEE, and you also have to deal with the IO security. So this is a very interesting interesting problem, and so we, with my students, we did a very initial efforts. That was 5 years ago, and today, like I said, we still actively investigate this direction. And also interestingly, in last year CCS, we also noticed our researchers also actively, keep pushing the boundary of using TEE for game protection. And in particular, they demonstrated you can use TEE to protect some secret, like the map of the computer games by using TEE. So what I've talked about, right? So today, basically, I explained to you guys a couple of efforts my students and my group and also my colleagues we have worked on of using trust execution environment to achieve confidential computing. In particular, I talk about the big matrix projects, briefly mentioned that, and also how to make sure code secrecy and how to develop memory safe SDKs, and also how to what's the challenges if you want to apply for game protection. And I hope I have convinced you TEE is interesting, and meanwhile, it's a promising direction towards confidential computing. And of course, I have to thank many people involved in this project, particularly the students and my colleagues and also my collaborators from industry. And of course, I have to also thank the National Science Foundations in support of my research in this direction. And with that, I think I thank you for your attention. I would like to take questions.
So thank you, Dr. Lin. I don't see any questions showing up in the chat just yet, so I'll give folks a couple minutes to bring their thoughts together, but I do have a question for you. So in your example with respect to sharing of SGX protected medical records, I'm just wondering how you actually approach this given the complexity that exists in that system. So the HIPAA compliance and doing so in a regulatory environment. So could you address the other hurdles that you may have to?
Absolutely. This is a huge problem, right? Because all the regulations involved, because medical record is so sensitive, right? So here I was just illustrate it's possible, but definitely require a huge amount of efforts from many parties involved. Right now, we haven't seen any, research that has make this happen. So here I was just saying, perhaps as a community, we can work together. We can achieve this vision of using TEE for practical sensitive record sharing. I see our chat in question in the chat. So
yes. So Tasso.
Yep.
Question is, why did you choose to pursue these projects, and what makes you excited or interested in this?
Great question. So my personal interest is mostly on program analysis. So my dissertation or my early work is all focused on reverse engineering binary code to find secrets, to find malware, all find vulnerabilities. But when this SGX hardware come out, you realize operating system cannot look at secrets, debuggers cannot understand the code. So eventually it's become black box. That means eventually we must understand this technology. And then we realize, hey, this is, can we use this to do anti-cheating? That's why I was so excited about those anti-cheating projects. And if we solve that problem, you can apply the solution in that problem to many other applications. And for data analysis projects, so I'm not an expert. That's why I collaborate with my colleagues. They are the experts. They bring domain the domain problem. That's why we work together. Right. Hope I have answered your question. Yeah.
Great. Thank you. Another question from Daniel Gratz. Is this specific to Intel processors? Is there a way this could be used for other processors, such as in iPhones?
It's a great question. So I only use the Intel processor as the example, right? So actually there are AMD processors called AMD SEV and also the ARM TrustZone. They all can be used. So like I say, your phone actually has TEE built-in. So it's just a matter of how the community, right, leverages technology and to protect the secrets of anything you can think about.
Okay. Are there other questions? If you would like to unmute, we could do that. Just put that request in the chat. I'll give you a second to do that. Jenny Grabmeyer put a question in the chat. What impact does TEE have on resource needs for processing?
Could you elaborate your question a little bit? So you talk about the computing resource or the target you want to protect? The energy?
Sure.
Okay. So you're referring like how much energy it will cost to process data using TEE? If that's the case, so they won't cost huge amount of resources. It's just a CPU features, right? In the commodity hardware, like in my laptop or desktop, I don't see any like my energy bill increase. It's just a computer, and the key technology there is memory encryption, right? You can imagine it's just somehow maybe there are additional operation going on. The hardware takes care of your encryption, decryption, and hash. So right, we wouldn't say much energy, or other resource consumption there.
Okay, we have another question from Zhiqiang. Is it possible that your effort can be overcome and compromised?
Great question. So as a security researcher, we all understand security is especially defense side, right? It's so hard, and always attackers can find holes to poke your system. But on the other hand, we understand, right? The foundation technology for TEE is built on top of cryptography, and they have strong theory there. And in terms of practice, definitely, right? You have a great tools. If you don't use it properly, like you leak your secret, leak your cryptographic keys, this is not secure, right? It's a huge amount of problem there. So, but definitely this represents our direction to work on.
And Tanya Berger-Wolf has a question. Can you talk about the trade-offs between the security and method performance, accuracy, speed, etc.?
Okay, right. That's a great question. So always security has a trade-off, right, between other metrics. Because security is the negative side of the system, right? It's like you deal with adversaries, and super strong security system maybe require extra resources to protect it, and you always balance our trade-off. Right, that's is always, in security we look at, like, we always start from your threat model and to see how much budget you have to understand what kind of adversary you're dealing with, right? There's no like a bulletproof super secure system, and so here, if we come back to talk about the TEE technology here, and definitely you need a new investment, right? Investment of the hardware technology and also software. You have to either redevelop your software by embracing this technology, or how to handle my legacy investment, how to handle I have a huge amount of legacy software, right? How can I run my legacy software with this technology? So there are lots of problems to solve. Yeah.
Okay. And that's it for the questions. Dr. Lin, thank you very much for your fantastic presentation today. We appreciate it.
Thank you.
Thank you. Okay, our next speaker is Dr. Raef Bassily. Dr. Bassily is a TDAI core faculty and assistant professor in computer science and engineering. His research focuses on tackling current challenges in data analysis and machine learning, especially those of direct impact on society. His research efforts are devoted to developing practical algorithms with formal privacy and utility guarantees for fundamental problems in machine learning and data analysis. Through his interdisciplinary work, he employs tools and ideas from learning theory, optimization, information theory, and statistics, among others. Before coming to OSU, he was a postdoc fellow at UC San Diego and Penn State, and he received his PhD in electrical and computer engineering from the University of Maryland, College Park. Today, Dr. Bassily will be talking about harnessing public data and privacy-preserving machine learning. Dr. Bassily.
Thank you. Thank you very much, Cathie, for the introduction. And thank you, everyone, for giving me the opportunity to talk a little bit about my research in the seminar. So my talk today is about harnessing public data in privacy-preserving machine learning. And perhaps let me start with a little bit of motivation for privacy-preserving machine learning in general. Perhaps one of the most prominent features of our modern times is, of course, the dissemination of large volumes of personal and sensitive data. And despite, of course, the huge societal benefits that we can reap by analyzing, learning from such data, the powerful tools of modern machine learning and data analysis can lead to real threats to personal privacy. To perhaps better understand the nature of these threats, let me talk a little bit about this basic model for private data analysis. So in this model, a data set comprised of personal and potentially sensitive data records, where here each data record represents one individual's data, is collected and maintained by a curator that has the capability of running various data analysis algorithms. And the goal here is to allow various users, such as government agencies or researchers or businesses, to learn useful information about the underlying population from which this data was sampled. For example, such information can be in the form of summary statistics or machine learning models that capture some global patterns in the input data set. The main challenge here is that a user may abuse the results of such analyses to try to extract sensitive information about some individuals in the data set. And this is indeed possible with the help of side information that this user can collect about the target individuals from external information sources like the internet or social media or other public data sets. In that sense, a legitimate user can itself be an adversary whose goal is to attack the privacy of some individual in the data set. Note here that this type of threats is quite distinct from the security threats that Zhiqiang was talking about in his talk. In particular, these threats will remain persistent even if the curator was secured and trusted. The goal of this area of research is to offer algorithmic solutions that enable releasing useful and accurate analyses of personal data sets while maintaining the privacy of individuals in these data sets, namely to achieve high utility while maintaining privacy. And these two goals are seemingly at least at odds. And this is what makes this task quite challenging. Well, before I tell you about a formal approach toward the privacy problem, let me briefly mention some of the reasons that makes the privacy problem a difficult one. One thing that has become quite evident in the last 2 decades is that ad hoc approaches that seems reasonable, like anonymization, are usually unsafe. In fact, this was demonstrated by actually so many real-life examples where attackers were able to re-identify individuals in supposedly anonymized data sets. And these attacks are mainly possible due to the ubiquity of personal information. Like I mentioned before, this ubiquity offers a wide range of auxiliary information to the attacker. And these external information sources can offer alternative identification capabilities to the attacker through perhaps attaching other attributes to any given individual. For example, an individual sometimes can be identified using a surprising collection of attributes, like, for example, some of the names of the movies they watched and approximate dates of watching these movies. On the other hand, even releasing functions of sensitive data sets or aggregate computations over sensitive data sets can leak information that may lead to privacy violations. Let me briefly mention 2 examples of this type of scenarios. The first is what is called membership inference attacks, especially in high dimensional statistics. For example, in a high-profile research paper that appeared in 2008 in phylogenetics, Omer et al. Actually showed that in genomic studies, under certain technical conditions, certain aggregate statistics of genetic data can be used to re-identify individuals in the study. that participated in the study. And it's not hard to see that this type of information leakage is actually a privacy violation, especially if that study was about some perhaps socially stigmatic disease. Actually, this finding has been taken very seriously by the scientific and medical communities. And in particular, there were drastic measures taken by the NIH, including restricting access to these statistics. Actually, previously, these statistics were open to the public. And the bottom line here is that these restrictions usually constitute impediments to the advancement of science. And so basically the morale of this story is that if there is a rigorous and sound approach by which we can release these statistics in a privacy-preserving way, then this can lead to open science, which is of course a very desirable thing. Another, perhaps a pressing issue that recently garnered a lot of attention in machine learning research is the issue of memorization in neural networks. For example, recently, a team from Google showed that certain generative models for natural language can memorize sensitive information like social security numbers. I just wanted to note here that there are a lot more threats and attacks related to the privacy problem that are too many to survey here. And this slide does not even skim the surface of these issues. There is a large body of work that discusses a wide range of these issues in detail. I'll be happy, of course, to offer some resources and citations offline. The last decade has witnessed the rise of a sound mathematical theory for privacy-preserving data analysis known as differential privacy. And this theory offers provable privacy guarantees and gives rise to a rigorous framework for designing algorithms that enable learning about the population without learning about individuals. And this framework also offers or allows us basically to reason about privacy in a quantifiable fashion. This framework also has many desirable properties that simplify the algorithmic design of complex systems that require stringent privacy guarantees. That's why differential privacy has become the gold standard of privacy-preserving data analysis and machine learning. Differential privacy has also been successfully adopted in industry by companies such as Google and Apple, and also by government agencies such as the US Census Bureau since 2020. So what is differential privacy? At a high level, differential privacy is a constraint on computations over sensitive data sets. It implies that a single individual in the data set cannot have any noticeable effect on the output of the computation. So intuitively, this means that one cannot infer the presence or absence of any given individual in the data set from observing the output of the computation. Let me try to give some intuitive description for the mathematical definition of differential privacy. Consider a randomized algorithm running on a sensitive data set and imagine two scenarios. Suppose in the first scenario, the input data set contains your data record, whereas in the second scenario, the input data set is the same except that it doesn't have your record. So here, in these two scenarios, the two input data sets are the same except that they are different in one individual's data record, your data. So we say that the randomized algorithm is differentially private if the distributions of the output of the algorithm in these two scenarios are close to each other. You can see differential privacy is a distributional indistinguishability constraint of over the output of randomized algorithms when run on neighboring data sets that differ in one individual's data. And you can see that this is aligned with the intuition I mentioned earlier, that basically one cannot infer from the output of the algorithm, whether we are in scenario 1 or scenario 2. And hence, one cannot infer the presence or the absence of your data record in the input data set. So this closeness in the distributional indistinguishability constraint, the closeness between this distribution is measured by two privacy parameters or privacy knobs, which are usually denoted as epsilon and delta. And these privacy parameters quantify the desired level of privacy. Smaller values of this parameter means higher level of privacy. For semantical reasons, which I'm not gonna get into today, epsilon is typically chosen to be a small constant, say 0.1, and delta should be chosen to be much smaller than the inverse of the dataset size. It's important to note here, though, that differentially private algorithms must be randomized, meaning that they must involve some form of internal randomization, for example, through noise injection in the computation. And this would generally lead to additional error. And the most basic question in this area of research is how to design differentially private algorithms with the least amount of error possible. One particular area where differential privacy has played a central role is privacy-preserving machine learning. And at a very basic level, here we have a private and sensitive data set, or training data set. And the goal is to design a learning algorithm that produces a predictive model based on this data set, such that the resulting model does not leak information specific to any individual in the input data set. And this is exactly what differential privacy guarantees. So the meta goal here is to design a learning algorithm that satisfies the notion of differential privacy, or in other words, to design differentially private learning algorithms. Classically, without any privacy constraints, one of the most fundamental questions in machine learning is concerned with understanding and characterizing the trade-off between the number of samples in the input data set and the prediction accuracy of the output model. In privacy-preserving machine learning, we add a new dimension to this trade-off. Here, our fundamental goal is to design differentially private learning algorithms that achieve the optimal trade-off between privacy, accuracy, and the number of samples. Despite its remarkable progress, the differentially private machine learning has actually several limitations that manifest themselves in various settings. For example, in a broad range of machine learning problems, the error incurred by differentially private learning algorithm is actually shown to scale, sometimes even necessarily scale, with the dimensionality of the problem, which is often equivalent to the size of the output model. This can lead to modest to even poor performance, especially in modern machine learning settings, such as in deep learning. On the other hand, we know that the analogous error guarantees in the non-private setting without any privacy constraints is often free from such dependencies. Another manifestation of such limitations appear in the formal model of PAC learning, probably approximately correct learning, which is one of the most fundamental and theoretical models for machine learning. It's basically the theoretical father of machine learning. And there are several impossibility results in the literature of differential privacy showing that PAC learning of even simple hypothesis or functional classes, like even one-dimensional threshold functions, is impossible under differential privacy. On the contrary, learning such classes are quite simple without privacy constraints and can be done using few training examples. So these limitations motivate our study of a relaxed model of differentially private learning, where in addition to the input sensitive training set, the learning algorithm has also access to some amount of data that entail no privacy constraint, which I will refer to as public data. In a recent work, we formalized this model in the context of supervised learning. And in this model, the learning algorithm, which we call here public data assisted private learning, or PAP learner for short, takes as input two data sets. One is private and is often labeled, and the other is public and can be either labeled or unlabeled. And the goal is to design algorithms that can circumvent the limitations of the conventional model of differential privacy and attain comparable accuracy to non-private learners, using only a limited amount of public data, while at the same time provide strong privacy guarantees for the sensitive training set. So note here, a PAP learner is required to satisfy differential privacy, but only with respect to the private data set. In my work in this direction, we consider two approaches to design such algorithms for classification problems mainly. So we'll focus on classification problems. One approach is a black box and the other is a white box. Let me tell you a little bit about these two approaches. In the black box approach, we basically bootstrap a PAP learner using only black box access to any generic non-private learner with good accuracy. And our algorithm requires only unlabeled public data. And the size of the public data set is roughly the same as the sample complexity of non-private learning, which is basically the minimum number of samples required by the non-private learner to output a good classifier. Our algorithm provably learns any functional class, any hypothesis class, with accuracy comparable to the accuracy of the non-private learner. Although the accuracy achieved in this case is slightly worse than the accuracy achieved in the non-private learning setting. Our algorithm also is computationally efficient as long as the underlying non-private learner is computationally efficient. The white box approach is different in the sense that we design PAP learners from the scratch rather than using a non-private learner as a black box. So this approach may not be as practical as the first approach because it doesn't enable us to reuse existing non-private learners. However, our goal there was to nail down the fundamental limits of private learning under this relaxed model in terms of the private and public sample complexities. This approach also, or our construction in this approach, requires only unlabeled public data, and actually the amount of public data needed under this approach is much less than what is needed in the first approach. And we can also show that we learn any hypothesis class, but even with optimal accuracy, this is even better than the first approach in terms of accuracy. And the accuracy we attain here is essentially the same as the accuracy that we can attain in non-private learning. However, one major drawback is that the construction we have so far are basically theoretical constructions, and they can be computationally inefficient in general. In the remaining minutes of this talk, I'll tell you a little bit more about our algorithm that follows the black box approach. Our algorithm has two stages. Just to remind you, here we have a sensitive training set, which is labeled, and a public data set, which is unlabeled. So mainly we have a bunch of public featured vectors and a sensitive labeled training set. And in the first stage, we build a differentially private predictor, denoted here as APRIV, that uses the private training set to provide privatized labels for the unlabeled public data set. So APRIV here is built using a black box access to any generic non-private learner with good accuracy. In particular, as we'll see shortly, we post-process the outputs of this non-private learner in a differentially private manner to generate privatized labels for the public feature vectors based on the sensitive and private training set. In the second stage, we use the newly labeled data set, mainly the data set of the public features vectors and the private labels, to train any generic non-private learner, again with good accuracy, and finally output a classifier. In that sense, the second stage is a mere post-processing of the output of the first stage. In particular, we do not use, in the second stage, we do not use the sensitive training set again. And since differential privacy is closed under post-processing, the final classifier is safe to publish from a privacy perspective. Our construction follows the so-called knowledge transfer paradigm, which has been used in previous works. However, our work offers two main contributions compared to prior work. The first is that our construction involves new design tools based on some advanced tools in differential privacy that allow us to efficiently manage the privacy budget and hence attain significantly less privacy loss over the course of the algorithm, over the duration or the execution of the algorithm. And secondly, we provide actually formal accuracy guarantees for our algorithm in terms of sample complexity bounds. Now I'll give you a sneak peek of the construction idea for the first stage, namely our differentially private predictor APRIV. The first step is to partition the private training set into a number of disjoint chunks of equal size. And then we use each chunk to train your favorite non-private learner as long as it has a good accuracy, so any generic non-private learner. And hence, we end up with a collection of models or classifiers, okay? One for each chunk, basically. Now, for every unlabeled feature vector in the public data set, we obtain the labels produced by these classifiers on that feature vector. Then we compute basically the count of zeros, the count of 0 labels versus the count of 1 labels, and then compute the margin or the gap between the count of zeros and the count of ones. Now, when this margin is large, this means that the majority vote will be stable with respect to small changes in the input training set. So following the definition of differential privacy, intuitively we would expect it to be safe to output the majority vote when the margin is large enough. However, we cannot make such a decision based directly on the actual value of the margin because this value itself is a function, could be a deterministic function of the private training set. So doing so is not differentially private. So instead, what we do is that we test for stability in a differentially private manner. In particular, we add some amount of noise to the margin, and then we test whether the noisy margin is large enough. If yes, then we safely output the majority vote. If no, we output a random label. And from the properties of the noise, which is added namely to satisfy differential privacy, we can show that when the actual margin is sufficiently large, then with high probability, the predicted label, the final label, will be the same as the majority vote. Moreover, if the underlying non-private learner is accurate enough, then the majority vote will be the correct label, the true label. And this shows that we can actually attain accurate prediction. One important aspect about this construction is that the privacy budget, which is kind of captured by the privacy parameter epsilon delta, is consumed only by the unstable predictions, where the margin is low. No privacy cost whatsoever is incurred for the stable predictions, where the margin is high. And this allows us to use a privacy budget more efficiently and hence generate a large number of accurate predictions. Finally, we can formally transform the accuracy guarantees of the underlying non-private learner into accuracy guarantees for our private predictions. In particular, suppose that the misclassification rate of the non-private learner is at most some fraction alpha, then we can show that the misclassification rate in our private prediction is only a constant factor large, in particular at most 3 alpha. Once we generated accurate labels for the public data set, we can move on to the next stage, as I mentioned earlier, where we use this new data set as a training set for any generic non-private learner that will ultimately produce a classifier. And we argue formally in this work that the accuracy of the output classifier is comparable to that of the non-private learner. Okay, let me conclude. So of course, data privacy is a major challenge, especially in the light of modern practices of data analysis and machine learning. And differential privacy offers a rigorous algorithmic framework for data privacy centered around a sound mathematical theory and a definition for privacy. And despite its remarkable progress, the area of differentially private learner has several limitations. And to circumvent this limitation, my work, or one component of my research, formally introduces and studies a relaxed model for differentially private learner, where the learning algorithm has access to some amount of public data in addition to the sensitive training set. And we study 2 approaches for designing algorithm under this relaxed model: a black box approach, which I presented today, which is practical and efficient and attains a reasonable accuracy, and a white box approach based on other work of mine, where we do attain optimal accuracy and show that we can even use much less public data. However, our constructions there are basically theoretical constructions, and they can be computationally expensive. So thank you very much for listening. I'll stop here and I'll be happy to answer questions.
Great. Thank you for the great presentation, Dr. Bassily. We do have some questions in the chat. So a multi-part question from Tanya Berger-Wolf. I'll start with the first part. How vulnerable are these approaches to privacy attacks where the attacker can choose additional, possibly public data to break privacy?
So that's actually a wonderful question. So here, the notion of differential privacy is actually immune against any side information. So that's even without public data or not, even if the attacker knows everything about every data record in the data set except the target individual, still differential privacy offers a meaningful notion of privacy. So that's one of the main reasons differential privacy is very successful, because it's immune against side information. So the notion of differential privacy here is that the promise of differential privacy is that the same conclusions will be reached about any individual, regardless of that individual's data was part of the input data set or not. So differential privacy is not particularly a hiding approach, but it's an approach that aims at hiding information, but it just gives this sort of differential promise, basically that whether or not. So it's basically, it tells every person, it gives every person an incentive to share in or contribute their data in a given study by saying that, well, regardless of whether you're going to contribute your data or not, the same conclusions will be reached. So if this public data is out there and there is still a risk of being disclosed, differential privacy will basically imply that the same conclusion will be reached anyway. So if one of the persons or one of the individual's data in the private data set was deemed to be disclosed based on that public data out there anyways, then differential privacy will not add an additional risk to that. So this is basically the answer to, I hope that kind of clarify this or answer the first question. So the second question.
Oops. The second part of that is also, does this approach generalize to temporal, longitudinal settings where data are time series of records and there is predictive value in the temporal information?
That is indeed a wonderful question. The main issue, I mean, in principle, in theory, this approach can be extended to time series using perhaps some additional techniques from the differential privacy, like the binary tree algorithm, and that is tuned to time series data, and some other tools from differential privacy. However, the main issue there is the how to manage the privacy budget, and the fact that there is an underlying information recovery law that says as much as the longer we process data, the more information will be leaked anyways. So the main challenge there is to design algorithms that have the best tracking or the best management for the privacy budget that attains as small privacy loss as possible over a certain time window. So, but of course, there are also some algorithmic challenges in this approach. But in principle, yes, this approach can be at least used as a seed for perhaps a more sophisticated system that takes care of this kind of settings. Does this answer the question? I hope it answered it.
I think so. I don't see any other questions in the chat. Folks can unmute or request to be unmuted if you'd like to ask a question in person. I'm going to give folks a second. So I'm not seeing anything come up in the chat. So oh, Tanya, do you want to unmute? We can do that for you.
There we go.
There you go.
I have a voice. So, Raef, I wanted to follow up on this. How directly applicable, because there's a lot of the implicit assumptions about whether the distributional privacy is approached. So can you talk a little bit about when it is not the right approach, and maybe, and I know Cathie needs to leave, so I can stay as, at least in voice, hosting the.
Definitely, definitely. No, of course. So one of perhaps of the settings or a domain of applications where differential privacy perhaps is not the right approach or not give the right semantics to the problem is for perhaps personalization. So basically in scenarios where you want to provide a certain services to one individual based on their own data. So in this case, differential privacy may not be the right approach because differential privacy is mainly designed for settings where we have a large data set, a bunch of individuals, and we want to produce some aggregate information that captures some underlying patterns in the population from which this data set was sampled. In the settings where we aim to give sort of personalized data-driven services, differential privacy is still like, it's questionable whether this is the right approach to use. And so again, like it's all based on the semantics of differential privacy. It always gives this, differential promise that, or differential or relative guarantee that basically at the end of the day, the same conclusions will be reached whether one person's data is included in the data set or not. Another thing is perhaps it's given in the light of the recent developments and COVID, of course, in situations where we really kind of like want to ensure almost perfect accuracy, then there is a question whether differential privacy would be the right, would be suspicious. For example, in contact tracing, there is a question, of course, whether differential privacy would be the right approach. For example, in this kind of situations, we definitely need, we cannot afford some internal randomization. We definitely need to understand and track individuals who were exposed to COVID-19. So again, like in situations where we wanted to release general statistics that capture something underlying global patterns in the population, differential privacy is a way to go. But for things, scenarios or applications where we do need perfect accuracy and things that kind of like is tied to personalized, more personalized settings, then perhaps differential privacy is not the right approach in this case. It's not the right definition.
Thank you. And I think with that, I don't see I don't see any.
One question in the Q&A. One last question in the Q&A from Dustin.
Oh, great.
Sure. Have you attempted to attack existing systems? Oh, yeah, that is a wonderful question. I think the way I understand the question, have we attempted to see if our approach is resilient to attacks? This is actually has been, there are certain empirical works that came after some of this work actually was concurrent to ours, and some of them was actually prior to our works that conducted some empirical studies. And some of these studies were actually conducted by some teams from Google, and they basically showed that using this approach kind of like satisfy differential privacy, and hence differential privacy is in itself is this information theoretic guarantee, so it's resilient to any kind of attacks. It does not unlike the security threats, it does not rely on computational assumptions. So yes, there has been some empirical works that looked into the use of differential privacy and specifically similar models to ours in order to provide systems that are resilient to attacks on privacy. Okay.
Well, thank you very much.
Very welcome, and thank you for having us.
Yeah, this is, and the recording will be available on TDAI website. So for those who were not able to participate and attend directly, Dr. Lin's and Dr. Bassily's talk, they will be able to follow up and hopefully follow up with questions if there are any. Thank you.
Thank you.